In that case, I guess I can get started. To the attendees in the live audience, please feel free to interrupt me. I like knowing where my audience is at. There is no such thing as a stupid question when it is asked in good faith. This presentation was made to be delivered at universities in China, which is why I have a Chinese translation or transliteration of my name. Fortunately for English-speaking audience, my surname is quite easy to read already if you use the Latin characters. So that's Alan Shipyangets. And feel free to send me an email. This is joint work with Ferdinand, who's the lead developer on Triton-VM, and Torkil, who is co-founder with me over at Neptune. By the way, Neptune is a new layer one cryptocurrency big on privacy. We are bringing ZK Starks to layer one, and the concrete ZK Stark prover and verifier and virtual machine that we are bringing to layer one is called Triton-VM. And so Triton-VM is the pillar on which we are building this blockchain, but you can also use it without having to use Neptune. You can use it as a standalone virtual machine and prover and verifier. And so that's why there are two brands on this slide. The presentation is divided into 4 parts, but I'm afraid that we probably won't have time to get to the 4th part. Let me set the timer. It's because the previous time I gave this presentation, it clocked in at 70 minutes for all 4 parts, and I'm not sure what the correct time is for this one. So I'll just be targeting 1 hour. And if I don't reach 1 hour, I can cover the last topic. And if I'm over, then I'll hurry up and maybe drop the last topic from this table of contents. So as I was saying, the presentation is divided into 4 parts. In the first part, I'll just be covering the basics of zero-knowledge virtual machines. Then I'll be covering the basics of Starks, and then I'll be covering the basics of Triton-VM. So this is a progressive refinement of focus, because the first chapter is very general, then it's slightly more specific, and then it's very specific. And then the 4th chapter, if we get there, is stuff that we intend to do in the future, but have not implemented yet. So SNARKs are succinct, non-interactive arguments of knowledge, and you don't really need to know what the acronym stands for. You just need to know that from an abstract point of view, we are dealing with machines that take an input to an output, and if the machine is universal, then that means there's some program that's sometimes considered to be part of the input, sometimes considered to be separate. But the point is that this program contains all the logic by which the input is sent to the output. And so it gives rise to a very simple diagram. But we want to simulate this machine on a computer. And then we have a virtual machine, because it doesn't exist in real life, it only exists on the computer. And if we record the state of the virtual machine at every point in time, then we have a list of states, and this list of states. Yes, please.
Yes, I think the slides are not moving. We just see like the first presentation slide. There.
I see. That's not good. Okay, now you do see it.
Yeah.
How about I just present without full screen mode from the window like so. And by the way, now I can read the chat. So if anyone has a question and they're too shy to let their voice be heard, then I can also read from the chat.
Okay, thanks.
Right. So I was saying, from an abstract point of view, we have the input that is sent to the output by the logic specified in a program. And the virtual machine computes this transformation. And if we record the state at every point in time of the virtual machine, then we have a trace. So the trace is a list of states. And the idea of proof systems in general, and especially proof systems capable of arbitrary logic, is that we separate this picture into two parts, the prover and the verifier. So the prover takes the input, the program, and the output, and in addition to those three, it takes the trace, and it outputs a proof, which is a short string of cryptographic data. And the verifier takes the input, the program, and the output as input, and also the proof as input, and outputs a 0 or 1 depending on whether the proof is convincing. And in a proper proof system, the proof is convincing if and only if the claim that the input is mapped to the output under this program, if that claim is correct.
Mr. Allen, I'm sorry. I think we can't see the whole slide again, unfortunately.
That's not good. Right. Let's do this. I probably have the slides on my phone, and then I can send them to Diego, who can present it from his computer. Let me find that. Yeah.
Actually, when you first toggled out from the full screen, we could see it actually. If you can take it back to the smaller part, or I don't know what you have done before.
But it is out of full screen, I'm afraid.
Yeah, but I think that the screen just cut and we get like 1/4 or something. If not, if you send
Are
it
you
to
seeing
me.
that left or the right? Yeah, I'm afraid I don't have it on the phone. I probably can connect to the VPN real quick, send it over, and then disconnect again. I'm wondering if that's the smartest course of action. I don't see any other way. So let's try that.
Yeah, I think that's because you reduced like the screen or the size of the screen so that we could see, you could see the chat. Maybe if you just, there, we see it perfect.
Okay, that works as well. But does it work if I toggle?
Yes.
Yes.
Are you
yes.
seeing this animation? Perfect.
Yeah.
Amazing. Okay, then we can continue like so. And so in general, we split up this computation into the prover and the verifier. And the reason why we split this, why we make this split, is because this unlocks features, useful features, namely succinct verification, which means that the verifier can work far faster than the prover, faster even than it takes to execute this computation naively. And secondly, zero knowledge, which means that the prover and the computation in general happens relative to some secrets that the verifier does not get to have access to. And this is useful from a cryptographic point of view because sometimes you don't want to leak sensitive data. All right, so that's from a very abstract point of view. Let's try to make this concrete with a game known as Sudoku. I want to prove in zero knowledge and succinctly that I have a solution to this Sudoku. And here's one way I might go about doing it. So a Sudoku, if you don't know, it's a single player game where you're given a grid of 9 by 9 empty boxes and some numbers are filled in. And you have to complete this grid by filling out the numbers 1 through 9 in every row, every column, and every block. And it's kind of difficult, especially if the numbers that are given are chosen to make it as difficult as possible. it can take you, well, if you don't know how to solve Sudokus, it'll take you forever. If you're experienced solving Sudokus, it can take you several minutes. And so I want to prove to you that I have a solution to this particular Sudoku. And here's what I can do. I can draw the numbers on cards and put the cards in their right location face down. That gives this picture. And you, as the verifier, you get to select one row, one column, or one block. And then you collect those cards. I verify that you shuffle them before flipping them. And when you flip them, you check that the numbers 1 through 9 are present. Now, if I'm honest, then the numbers 1 through 9 will be present in every single case, regardless of your choice. But if I'm malicious, then there is a certain probability that my fraud will be exposed. And so what we do in order to make this check robust is we repeat this protocol. After you check that the numbers 1 through 9 are there, you give the cards back to me. I shuffle them again, and looking at the face where the number is drawn, I put them back in the right place. So this captures the intuition of zero knowledge, because you learn nothing about my solution because you're forced to shuffle. And it also captures the intuition about succinctness, because it's far less effort for you to verify my correct solution than it was for me to find it in the first place. And so that was the sketch of what it can do. Now here's a abstract application. All the applications actually take this form of verifiable outsourcing. So you, as a small computer, have access to a large computer, which we might denote by a cloud, and you also have a function and an input to that function, and you want to know the output to that function. This is very abstract from a computer scientific point of view. Everything consists of functions, but there's just some kind of computation that you want to be done. And you're happy to outsource it to the cloud. The cloud is happy to provide you with an answer, but how do you know that the answer is correct? Well, if the cloud might lie to you, then you don't. And so that's what you need a proof for. And it's really nice because snarks already guarantee that verifying the answer is faster than actually computing it yourself. So in this regime, it makes sense to outsource your computation to the cloud. And you might think, well, what if secrets are involved? What if this function f is a function of a public input x and of a secret input s? Can we still use the same principle? And the answer is yes, maybe, because it depends on who owns this s. If S lives on the cloud, yes, then we can totally apply a proof system, and it will be a zero knowledge proof system, and it goes through no problem. But if you, the outsourcer, know S and you're not allowed to reveal it to the rest of the world, then we have a problem. And in this case, we cannot use just zero knowledge proofs, and we have to rely on multi-party computation or fully homomorphic encryption instead. All right, that's the generic application that applies everywhere. Let's see some specific instances of this. First off, aggregation. This is in a blockchain context where we have a list of historical states of the blockchain and one current state. And I really mean the set of current accounts or the set of current unspent transaction outputs. The point is there are a whole bunch of transactions floating around, and there's a bit of a funnel being simulated in effect by the consensus mechanism, because everyone who participates in this consensus mechanism, be it proof of work or proof of stake, they need to verify all the signatures before they can include these transactions and update the state. And that's expensive. Not to mention that it costs a lot of bandwidth. And so with snarks, you can actually simplify this. Someone has to bundle all the signatures and they can replace the signatures with a snark proof that they were all verified and were all correct. But provided that they do this bundling, everyone else can verify that all the signatures were present and were correct, and they can straightforwardly, without hassle, apply the transaction updates. That's aggregating transactions. And another blockchain use case is rapid synchronization. And the idea is if you boot your computer and set it to synchronize with the network, Ethereum, Bitcoin, whatever network, you have to download all the blocks and verify them. And that takes a while. The last time I synchronized my Raspberry Pi to the Bitcoin network, it took me 2 weeks. Now, if we replace all of history of the blockchain with a stark proof that it was correct, then we don't need to download everything. We just download the stark proof and verify it. And verifying this can still be done in a matter of milliseconds. So down from 2 weeks to a matter of milliseconds, that's a great improvement. The problem is somebody has to compute this proof. All right, here's an application that does not pertain to blockchains, or at least not per se. Zero knowledge as a service exists. There's search engines, there's Midjourney, there's ChatGPT, and the idea is that you, as the end user, you upload your query to the machine learning server, and you get a response back. And that's great, but sometimes you want to know that the correct algorithm was used, or that the weights that are giving you this response are the same weights that are used to give other people the response, or you want to be assured that your query was used without modification. On my CV, it says that the Stark anatomy of a Stark is the first result that I get on Google if I press Stark anatomy. But I can't prove this, and other people might get other results first. So it's a little it's sad that I can't prove this fact and make my CV even more interesting. But with Starks or Snarks in general, you could do this. You could have a proof that's certified that the correct algorithm was used, even if that correct algorithm was secret, that the correct weights derived from the correct data set were used, even if those weights and data sets were secret. And the last application is really a killer application. It's because verifiable builds, let me restart. In the open source world, we have free access to open source software developed by other people, and we can audit it, we can install it and run it, and if we find a feature that we want to have and it's not there, or if we find a bug, then we can fix it. All of that is fantastic, but in practice, most of the software that we run and install comes packaged. And we hope that there is a link between the packages that we install and actually run and the software code bases that we can inspect on the internet. And it would be nice if this link were a little stronger, because maybe there's a discrepancy here. And by the way, this discrepancy is a serious national security problem, if you ask me. And so one solution is to compile it yourself. You download the code yourself, you compile it, and then you run it. That's hard and expensive, but some people are into that. With Bitcoin and Tor, they are using reproducible builds. So when you download the software, the packaged version is there, part of the software, and you can install that right away, but you can also verify that this packaged version is exactly the same as what you will get when you compile it yourself. And so if someone else doesn't get the same build, doesn't get the same package, they can broadcast this, and so there's some social consensus, social security about the fact that this package actually corresponds to the open source software. But still, someone needs to do that, and enough people need to do that, and it's expensive for them to do it. And so with verifiable builds, it would be really easy. You just look at the hash of the GitHub repository or wherever the repository lives, and you verify the proof. And then you have a proof that the software package that you're installing actually corresponds to the software that you're inspecting. That's great. All right, let me quickly look at the timer, which 18 minutes. Okay. So that was zero knowledge virtual machines. Let's look a little more specifically at Starks. Starks are a special kind of snarks. And one thing that sets them apart is the transparency. That's what the T stands for, which means that you don't have to trust anybody because traditionally snarks are defined through some kind of trusted setup ceremony. And if all the participants of the trusted setup ceremony are corrupt, then they can produce correct looking but actually fraudulent proofs. And with Starks, there is no such possibility. And so you don't have to trust any people. You just have to trust in the hardness of mathematical problems like the difficulty of finding collisions in a collision-resistant hash function. That's transparency, and transparency is the one feature that sets Starks apart from Snarks, and the other feature is that it looks at a state machine model of computation versus a circuit model of computation. So by state machine, I really mean this abstract flowchart diagram that we see in computer science. And the way it works is we need to find a description of this flowchart in terms of low degree polynomials over finite fields. So we have to define where does the state live. And here's an example. You might decide that this state for this particular machine or another machine, this is not a running example, so I don't think it makes perfect sense to use this state space for that diagram, but you get the point. These are just examples. Since we're dealing with polynomials over finite fields, the state space has to be a subset, at least, of a vector space over the same finite field. And so we can fix the initial state to some arbitrary point in this vector space. And the next step is we have to encode the logic for transitioning from the one state to the next state as some kind of polynomial in multiple variables of low degree. And this can be the transition function. And starting from the initial state, we have a sequence of next states defined by this transition function. This is the evolution of the state. All right, and then lastly, in order to turn this into a proof system, we need to have some kind of computational claim. And so in this example, I'm going to say that the x coordinate of the state after 7 steps of evolution is x star. That constitutes a valid claim. Well, maybe valid, the format is valid. Okay, so that's arithmetization. Now, how do we enforce the correct evolution? And how do we enforce the correctness of the claim? So once we collect all the states by applying the state transition functions, the state transition function singular, t many times, we have a table in which going down means going forward in time, and in which every column is one coordinate of the state space. We can interpolate these columns. That interpolation gives us trace polynomials, and this interpolation happens typically over some subgroup of order 2 to the k. Order doesn't really matter that much. The point is that the polynomial evaluated in some generator to the power I gives us the ith cell of that column. So in this way, we can switch between columns and polynomials without loss of generality. And now our constraints coming from the evolution and coming from the claim may be applied to polynomials instead of columns. And indeed, that's what we're going to do, right? We're going to translate the state transition function f into transition verification polynomials. And here's, so I wrote some example. These are rather arbitrary multivariate polynomials. But the point is that it's always possible to find this translation. You just take the, what is it? If you look at xy gets mapped to f of xy, the point is that there's a difference in time. So you get the subscript I and I plus one being the output side and I being the input side. And then you just move everything to the same side of the equation and you get an equation to zero. Everything in the left-hand side of that equation constitutes a new polynomial that is the transition verification polynomial, and it evaluates to zero in all points over which you are interpolating, except for the last row, provided that the evolution is integral. And so if you're presenting these verification polynomials with a trace that is not computed in accordance with the state transition function, it will evaluate to something different. So I'm already hinting at what's going to happen here. Yes.
That table, when we're talking about virtual machines, what you will have there is a list of mnemonics, probably with operands, right?
This table consists of finite field elements.
Yeah, but what will be the shape of that table? Where if the trade comes from the structure of a virtual machine? That's my question, actually. Because now we're talking about state transitions in a Turing machine problem.
Yeah, so in a, well, you can simulate a Turing machine with a virtual machine, and in fact, it's the two are not that far apart. We typically think of every column as tracking the values of a register across time. So if you have a von Neumann architecture defined in terms of 10 registers, then you would have 10 columns. Things get a little more tricky if you also have access to memory, but I'll get to that later. So yeah, we have these transition verification polynomials, and the point is that we compose them with the trace polynomials. And these are the composition polynomials, and their key features is that they evaluate to zero in the right points. They evaluate to zero in points that satisfy the correct evolution, which if we interpolate it over this subgroup will be the entire subgroup except for the last point, because at that point we don't care about the correct evolution anymore. So that's the evolution. What about the claim? Well, it turns out that the claim we can transform into a boundary condition, and the boundary condition, well, it also gives rise to a polynomial. This one happens to be in one variable, but you can extend this to multiple variables. And in order to require that this polynomial is satisfied, once again, we compose it with a trace polynomial. This trace polynomial evaluates to zero in all points that satisfy the boundary condition. And so what we're going to end up doing is we're going to verify that it does evaluate to zero in the one point that we're interested in, which is the 7th iteration, because that's what the claim said. We're looking at the value of the x-coordinate in the 7th iteration. So once again, we have this algebraic execution trace. We have these composition polynomials. And the first two composition polynomials have to do with the correct evolution. And the third composition polynomial does not have to do with the transition, it has to do with the boundary constraint. And so we know ahead of time that for correct traces, they have to satisfy a particular pattern of zeros. And where they're not zero, we don't care about their value. And with a little bit of algebra, we can trivially produce other polynomials that have the exact same pattern. These are the vanishing polynomials, or zerofiers if you use our terminology. And once again, we don't care about their value except when they're zero, but the point is we know that these vanishing polynomials evaluate to zero in the right points. And then using the second piece of algebra, it follows that the polynomials on the right have to divide the polynomials on the left. So we have to get a clean division here. This gives us the quotient polynomials, and then in the proof system, we end up summing all the quotient polynomials using random weights, thereby reducing the entire computational claim to a single polynomial. All right, so let's look at the part of the pipeline that we've touched so far. We started from a computation defined in terms of an abstract Turing machine, and we've arithmetized this, giving us a polynomial representation, and we've enforced the constraints, giving multiple polynomials, and then even reduced it to a single polynomial. And at this point already, a question that stands out is how do we even represent these polynomials? I'll get to that later, because how we represent those polynomials has to do with the last step of the pipeline, which is how do we prove that it actually corresponds to a low degree polynomial as opposed to a random bunch of points. And that's what Fry does. Fry, it proves that the last polynomial that we end up with is in fact a polynomial of low degree, and it tells us how to represent polynomials. By the way, what I forgot to mention here is that if this division fails, you can still plow ahead in the proof system and pretend as though it didn't fail, but then in the end you end up with a polynomial of high degree, very high degree. Whereas if this division is clean, then the quotient polynomials, and thus also the combination polynomial, is a polynomial of low degree. So you want this distinction between high and low degrees. And that's exactly what Fry gives you. Fry says, yes, okay, it was fine if the polynomial was of low degree, and it will say, no, it's wrong, it's false if the polynomial was of high degree. So it stands for Fast Reed-Solomon Interactive Oracle Proof of Proximity, but once again, the acronym does not really matter. Fry is fine as a standalone name. But the name gives presenters like me a segue into explaining how it works mechanically, because the fast is the same fast as in fast Fourier transform, which uses this decomposition of polynomials. Namely, you look at their vectors of coefficients, and then you look at the even coefficients and at the odd coefficients. And in fact, there is a description in terms of polynomials to compute the polynomials of even coefficients and odd coefficients themselves. That's the fast part. Now the Reed-Solomon IOP part indicates that we're looking at code words. And so we're going to take these polynomials and we're going to evaluate them over a large domain. This domain is much larger than the domain that we used for interpolation, usually by a factor of 4 or even 16 in some cases. And so we're going to represent the polynomial by a whole bunch more points given by its evaluations. And then we're going to compress this using a Merkle tree. So in this way, we reduce it to a single digest, which is the root of this tree. And we're going to do this over and over and over again, because the commit phase is actually a whole bunch of rounds in which we send one route to the verifier, get back randomness, and use this randomness to fold the two halves of the polynomial together. In other words, we compute a random linear combination of the polynomials of even and odd coefficients, respectively. That step is folding, and so we fold, compute Merkle root, get randomness, fold, compute Merkle root, get randomness, and so on, until we either have the constant polynomial or in practice we want to abort early. And so in every step, the degree of the polynomial shrinks by a factor of 2, and so you have a logarithmic number of steps needed in this protocol. But this is only the commit phase, because the only thing that the prover sent to the verifier at this point is a bunch of digests. In order to verify that these digests actually do represent correctly computed polynomials, the Merkle trees have to be opened, and they have to be opened in locations chosen by the verifier. And so the verifier sends indices, and every index in every code word has a brother, which is exactly n/2 locations further away, and it has a cousin in the next code word. So every index identifies 3 points, and you can derive a linearity condition, 3 points that have to be on the same line, if the next code word was correctly derived from the previous. And so you just test for this linearity condition. Now, these linearity tests are the bottleneck in how you get your protocol to be sound. And we typically use the right-hand rule. You get logarithm of rho number of bits of security per collinearity test, where rho is the rate of the code. You can also think of that as the ratio between the domain that's used for interpolation versus evaluation. And this is the dirty secret of Stark proofs in practice, right? We all use this right-hand rule that you get that you get log rho bits of security per collinearity test. But in practice, we don't have a proof of this. The only proofs that we have give you strictly less than 1 bit of security per collinearity test. And yet we still use this right-hand rule because, well, we think it's correct, it's conjectured to be correct, and we also don't know of any attacks that would indicate that it's not correct. And so one of the problems that keeps me awake at night is trying to find a proof for exactly this conjecture. All right, I mentioned earlier that the algebraic execution trace tracks the values of a bunch of registers, but things get complicated if you include memory. And typically you want to read instructions from a program which might live in memory or it might live elsewhere. And you also want to have some kind of input and output that you're interfacing to the program with or through. And so there has to be some kind of communication between the processor and external things. And so we know how to correctly describe the evolution within the processor. And if memory can be characterized as a coprocessor, then we know how to prove the correct evolution of memory. But how do we prove the correct communication? Well, that's what we use the two-stage separation for. In the first stage, we prove the correct evolution of every table internally, according to its own internal table-specific rules. And then in the second stage, we prove the correct interaction between the various tables. This works because the The added columns are randomized, and so we only get this randomness after interacting with the verifier, because otherwise it's not secure. And we also have randomized constraints. So with that said, here is what the entire Stark workflow looks like. We start from an algebraic execution trace, and we turn this into the main execution trace through low degree extension. We hash the rows of this table and compute a Merkle tree over that. The root goes to the verifier comes back with randomness, which we use to compute the second stage, which is a bunch of auxiliary columns. And once again, we hash the rows, compute a Merkle tree, interact with the verifier, and now we can compute the quotients. And since we interacted with the verifier, we are also getting weights to compress these quotients, because after all, they are supposed to evaluate to 0 on the same domains. Or, well, they're supposed to be low degree, right? The quotients happen, they're quotients because we already divided out the vanishing polynomials. At this point, we interact with the verifier again, but now the verifier gives us an out-of-domain point. You can think of this as an index that points out of the tables, because it's really an indeterminate. So every row in this table corresponds to omega to the power I, but the challenge from the verifier here is just an arbitrary field element. In fact, it's a random field element. So it does not point into the table. And the prover supplies the rows, quotation mark, rows of the tables in this point, which corresponds to the evaluations of the matching polynomials in that point. And for technical reasons, he has to provide 2 for the main and auxiliary tables. That's not an important detail. After the prover supplies this out-of-domain row, he can interact with the verifier once again and obtain weights with which both all the columns can be combined, and in the out-of-domain row, that out-of-domain row can be compressed into a single point. And now we apply the deep update, because we have one single column that represents a polynomial, and we know that this polynomial has to evaluate to the point that we computed below. And so we're going to we're going to enforce this evaluation condition using the deep update. And this is just another composition polynomial. We subtract the value that we know it has to reach in Z, and then we divide by the zerofier, which is the polynomial that evaluates to 0 in Z. It's the same trick that we used to compute the quotients earlier. Now we do it once, and now we have the polynomial code word, that goes into Fry. And so Fry consists of computing a Merkle tree, interacting with a verifier, folding, and so on. And all the way at the end of Fry, the verifier gives us a bunch of indices, and we have to open all the code words in those indices, including the code words associated with the main and auxiliary trace, as well as the quotients. If this were in front of a live audience, I'd say this is the slide you want to take a picture of, but this is an online audience, so you can take a print screen, and if you're watching this online, you can even pause and look at this in more detail. All right, that was Starks. Now let's look at Triton-VM. So Triton-VM is an open source project where we're happy to receive contributions. If you like Rust, you'll love Triton-VM. We have a website and a repository on GitHub. that's that. One thing that sets us apart from some other projects, not all other projects, is the prime field. We use the prime with 2 to the 64 minus 2 to the 32 plus 1 elements. We call it the Oxford prime. Other people mistakenly call it the Goldilocks prime. And we use it because of its structure. This structure means that it's very easy to compute modular reduction and even Montgomery reduction, which is faster on our machines. But it's also, so Montgomery reduction, but it also has a subgroup of order 2 to the 32, which means that the low degree extension step can be computed without too much hassle. And lastly, but not least, we have an efficient decomposition into U32s. So if I give you two U32s and I say these represent a valid field element, what I'm really trying to say is that if you concatenate their bits, then you get a number that's smaller than P. And because P has this fantastic structure, there's a very efficient way to prove this. And so going from field elements to U32s and back is very simple. And this is, in fact, the main reason why we use this prime. I had a diagram earlier of a processor interacting with input, output, program, and RAM. Our diagram is a little more complex. We have input, yes, we have output. We also have a program, but as the verifier of a proof, you only see the program hash. And so the program lives in a program table, but then the proof internally needs to verify that the hash that is the second part of the public input actually corresponds to the hash of the program. That's the program digest. And by the way, we have a separate table, a coprocessor for computing hashes. And so since we have that table, we're using that table to compute the program digest. This hash function is defined in terms of lookup gates, and to arithmetize that efficiently, we actually cascade into an intermediate table before we do the actual lookup. Aside from having a hash coprocessor, we have a coprocessor that's dedicated to U32, that's on the right. And then the last three tables on the bottom are memory tables. We have one for random access memory, then we have one for recording the location in the jump stack, return addresses, and whenever we call, we add to the jump stack. And we have another stack for operating, which is the intermediate values as you parse a formula, for instance. And by the way, the diagram didn't always look like this and probably won't always look like this going forward. This is what it looks like right now. So I mentioned the hash function. We're actually using a hash function that we came up with. Tip 5 stands for Triton Improvement Proposal 5. There were 4 improvement proposals before it. Tip 5 is a hash function. Yeah, it gave rise to this paper. You can find it on ePrint. And by the way, you can even look at the implementation because it's obviously open source.
How fast is it compared to Poseidon, Poseidon 2, and others?
It's about 9 times faster than Poseidon. It was not benchmarked against Poseidon 2. It's on par with Ketchak, but it is slower than Blake because, well, Blake is the fastest. And the reason why we have this performance is because we use lookup gates, and that allows us to shrink the number of rounds without compromising security. Now, we pay for these lookup gates because we actually have to arithmetize the correct lookup. And Poseidon has the advantage that you don't have to arithmetize the correct lookup. But then Poseidon pays for that by having to have a large number of rows, which reduces the speed. We don't have recursion yet, but it's a top priority in our roadmap. And the idea behind recursion is that we're taking the computation proof that we have from an earlier iteration, and we're turning that into the new input for a new computation proof. So the input, the output, and the program and the proof, they are jointly together the new input. And the program that we're going to run on this new input is the verifier. And since this verifier outputs 0 or 1, that is the new output. And so we can make the same diagram that I made earlier, where I separate a computation into the prover and the verifier. The computation is whatever the verifier does. We put this into the virtual machine. The trace of this virtual machine execution goes to the prover, who produces a proof. And this proof goes into the verifier, who verifies the correct execution of the verifier as it was verifying some computation. This has tons of applications everywhere, and we want to use it in Neptune to prove the correct verification of the previous block in every block. So since that block contained a proof, you have to verify it. Therefore, you have to prove the correct execution of the verifier. We make use of 4 cross-table arguments. It's actually not clear that the last one, the contiguity argument, is cross-table, but I listed here because of similarity in other respects. And out of time constraints, I'll only be looking at logups and the contiguity argument. By the way, if you understand how logups work, the evaluation and permutation arguments aren't too complicated. So how do logups work? The idea, the thing that we want to prove, remember, this is across tables. So this could be the hash function and the cascade table, or the cascade table and the lookup table, is we want to show that the set of rows of one table is a subset of the rows of another table. And in the first step, we just compress it using randomness provided by the verifier. Now we have a set of elements of one column living in one table, and this is claimed to be a subset of the set of elements of another virtual column living in another table. And we have to record explicitly the multiplicity with which these elements occur. And so in particular, since the row 4D occurs in the server but not in the client, its multiplicity is 0. And since the row 1A occurs twice in the client, its multiplicity is 2. And now at this point, we can extend in the auxiliary trace the client with a new column called the logarithmic derivative, which computes a running sum of reciprocals of beta minus the ith combination cell, where beta is another random scalar provided by the verifier. And so at the bottom of this extended column, auxiliary column, we get a large sum of 1 over something. And we're going to compute the same sum on the side of the server, except now we're going to multiply every term by its multiplicity. And so in the bottom of this auxiliary column, we also get a large sum of 1 over, some number over some complicated expression involving beta. And the point is that in the last cell, these columns have to agree. And well, if you want to convince yourself that they really do agree, you just multiply left and right hand sides with the product of all denominators, and you'll see that they do have to agree. As for memory consistency, this one is more complicated, because what we're trying to prove is that in between two accesses to memory at the same location, the memory value at that location did not change. And the difficulty arises from not having access to distinct points in time. We can only compare two rows, or maybe rows with a fixed distance between each other, but we cannot constrain memory accesses to that pattern of rows. And so the strategy that we have is we look at the clock cycle memory pointer or RAM pointer and memory value, RAM value in the processor, and we copy them over to the memory table, but there we sort them by address first and clock cycle second, whereas in the processor table, they are sorted by clock cycle only. This guarantees that all the rows with the same address are contiguous. They are not interleaved. And we need to show that we copied over the same set of rows, and we can use a permutation argument for that. In fact, we can even use a logup argument, but why would you use a logup argument if the thing that you're trying to establish is exactly a permutation? But this does not establish that the memory table was sorted correctly. And so we still have these 2 points to prove. And in the first step, we observe, actually, we don't need to sort by descending pointer value. We just need to establish that they are contiguous. So it doesn't matter if address A comes before address B or afterwards. It just matters that all rows with address A are bunched together and not interleaved with rows of any other address. And so we use a contiguity argument to establish this contiguity. And this argument relies on the Bézout relation. So we compute a running polynomial of a running product of x minus the ith memory pointer, where x is supplied by the verifier. And we simultaneously compute the formal derivative of this running product. And then we use a bit of algebra known as the Bézout relation. If the polynomial and its formal derivative, we compute their greatest common divisor, and their greatest common divisor is 1 if and only if no factors are repeated. And so we need to know what the cofactors are in this Bézout relation, but we can supply them. And then we just enforce the fact that this relation at the end of the table is satisfied. And then we know that there are no shared factors, meaning that no region of constant RAM pointer is entered into twice. All right. So that satisfies the first point. We've established contiguity by address. Now, how do we, excuse me, this should not be sort by RAM value. This should be, number 2 should be sort by clock cycle. How do we establish that? Well, all the clock cycle differences that are valid jump forward in time, not backwards in time. Meaning that they jump from one clock cycle that occurred in the execution of the program to another clock cycle that occurred in the execution of the program. And by the way, the processor records all clock cycles between 0 and the number of clock cycles that it ran for. So this difference has to live in the clock cycle column of the processor. And so we just prove that using a logup algorithm argument. All right, I have 3 minutes remaining, but then I guess there was a few hiccups with the presentation. Now is a good time to ask questions. but in principle, I can continue with the last chapter of the presentation, which should take some 10 minutes. And by the way, I'm also happy to take questions afterwards.
Just before moving on, right? How do you sort in that memory consistency check? How do you sort the columns? I've seen some people using just the sort by function from Rust, right? Or are you using some? Well, I'm asking because
using sort by.
Yeah, I'm asking because I was trying to do. There's this linear time algorithm for sorting, and I've been trying to like radix sort. I don't know if you know it. I've been trying to make that work and beat the sort by, but I couldn't manage to do it. Right. I was just curious about how you were doing it.
My intuition is that radix sort should work.
It should, right? I cannot make it work. Maybe my implementation is bad.
I don't know. I don't know off the top of my head which algorithm we're using, but I do know off the top of my head that this does not seem to be the bottleneck in practice, even though in theory you might expect this to be the bottleneck. The bottleneck in practice is hashing. And so I guess that has to do with relatively short length of the programs that we're running in practice. Because for sufficiently long programs, the entity and sorting will dominate, unless you use radix sort. All right, other questions? No other questions. In that case, let me move on to polynomial registers, which is an idea that we're toying with, we're brainstorming about and with, but we have not implemented it yet. And so the idea is traditional ZK-VM describes the evolution of a set of registers that take values from a finite field across time. And we're going to modify this idea. Now, some of our registers are still constrained to being finite field elements, but other registers can be univariate polynomials over this finite field. And we want to prove the correct evolution of this state. And so this allows us to use arithmetic on polynomials, which is strictly more powerful than arithmetic on scalars. So it has a potential here. And the reason why it might work is because after receiving randomness from the verifier, these polynomials collapse to their evaluation in alpha, where alpha is provided by the verifier. And so the error constraints, the constraints that enforce the correct evolution, they still apply, they just apply to the evaluations of these polynomials. But until we get this randomness from the verifier, we actually represent these polynomials symbolically. And there's no way to compress them. And that's the point, because we want to use a small number of instructions to enforce a very large number of evolutions in a very large vector, for instance. And one way that you might go about integrating support for this is by having the processor talk to a polynomial processor, and over this communication bus, they exchange polynomials, but then the polynomial coprocessor interacts with memory, and over this communication bus, they only exchange finite field elements. And so the polynomial coprocessor is responsible for concatenating polynomials, splitting them, and shifting them, is responsible for providing the processor with the evaluation of a given polynomial in a given point, is responsible for checking the degree and verifying it or supplying it to the processor. It's responsible for storing commitments two polynomials and providing them when the processor asks for them at the right time. And it's responsible for providing polynomials that are the Hadamard product. What is it? Polynomial C of x, if you look at the vector of coefficients, it's the Hadamard product or element-wise product of the vector of coefficients of polynomials A of x and B of x. And with respect to the Hadamard product, take my word for it, it's easy. With respect to concatenate, split, and shift, you probably don't even need to take my word for it. It's easy. But evaluation is slightly more challenging, and checking and querying degree, that's challenging but doable. But then how do you supply committed polynomials? That remains an open question. There is a trivial solution, but that's a solution that we're not happy with. So with respect to these three tasks that are not trivial, let me articulate some of the thoughts that we have. So, excuse me, before I do that, if these tasks were all doable, then we have a very, very powerful system because we can simulate any polynomial IOP inside the VM. And so that means that you can run the program and then run a Stark verifier or a Snark verifier on the side, or integrate that into part of the program, or you can run the program on a vector that you use another Snark to prove satisfies some other conditions. And by the way, you can also use this as part of the recursive verifier. You can also use polynomials and committed polynomials to affect continuations. That is what tip 8 is about, which is a improvement proposal. And obviously, and this was the whole idea that gave rise to the notion, you can affect single instruction multiple data. So already for addition, if you add two polynomials, it corresponds to element-wise addition of their vectors, of their coefficient vectors. But you can extend this to multiplication, and there are a whole bunch of single instruction multiple data operations that you can derive from operations on polynomials. And lastly, we need the low degree test to make it work, but once we have it, we can find tons of applications for it. So it's these applications that are really making us enthusiastic about this construction. So how do we evaluate a polynomial? So the processor says to the polynomial coprocessor, here's a polynomial, give me the value in y. Well, evaluation can be characterized as polynomial reduction by x minus y. And so if you reduce the polynomial f of x by the modulus x minus y, the remainder that you end up with is in fact the evaluation of f of x in y. And so the polynomial coprocessor is going to respond with r, but then he needs to prove that r is not a polynomial, it's a scalar, and concretely that means proving that the degree is 0. And he also needs to prove that some quotient exists such that f of x equals quotient times x minus y plus remainder. But all of these things are doable if we have the degree check. There are a bunch of degree checks, but if we have it, then we can do everything. All right, so how does the degree check work? Well, at this point, we need to have and track the values of a polynomial register that is a polynomial not in one indeterminate, but in two indeterminates. And the point of this polynomial register is that it is a running sum. As the virtual machine runs through its execution, it accumulates terms that are themselves univariate polynomials in X. And for every power of Y, it has one such term. So you can think of A of XY as the sum for, what is it? You can think of it consisting of a bunch of terms, every one of which is Y times some polynomial in X, where there is a power on the Y. And so we update these two registers whenever there is a degree check. We add one sum to the accumulator, and this sum is B of Y, where B tracks the kth power of Y, B of Y times F, and we also need to shift F. That gives us, so we check not that the degree is less than D, but is at most D. No, we check equality of degrees, not inequality of degrees. So there are, in every degree check, this accumulator accumulates two terms, and we also have to update the register that tracks the powers of Y. But that works. We also need to include this accumulator term in the random linear combination, because that's how we make sure it goes into Fry. And by the way, this when the verifier supplies alpha, we need to use this alpha as the value of the out of domain row. But under all of these conditions, it works. And then this is the trickiest part. How do we supply committed polynomials? If you look at how these polynomial IOPs work, at some point the prover needs to say, here's a committed polynomial, and it's the missing term that makes this equation go through. And it's difficult to do that with this formalism, because the constraints only authenticate the correct evolution of evaluations. They don't actually look at the polynomial as it was before evaluation. And so there's an attack that's always lurking in the background. You can pick an entirely different polynomial, except we ensure that it evaluates to the right values whenever its evaluations are queried. And the only way that we think we can get around this is to always ensure that we assemble the polynomials coefficient by coefficient, either from memory or from input or from some specific table whose only purpose of existence is committing to polynomials. There has to be one cell somewhere in the algebraic execution trace for every coefficient of this polynomial. And that's a bit of a bummer, because it means that you can add 1,000 elements, a vector of 1,000 elements to a vector of 1,000 elements in a single instruction, but you have to spend 1,000 instructions to build those vectors. Maybe it's not instructions, but those 1,000 cells in the algebraic execution trace have to live somewhere. And so the open problem that I'm going to close this presentation with is, can we do this in sublinear time? It's a bit of a bummer that we have to spend this 1,000 algebraic execution trace cells somewhere, and we'd like to spend less. Can we soundly assemble a polynomial of higher degree in less time than the number of coefficients that it consists of? And in order to assemble this, we have access to a bunch of things. We can, in fact, use vector instructions, because we have this whole polynomial coprocessor thing. And we can use evaluation queries and degree checks And these are powerful tools that we can use. We can even use pseudo-randomness, although this is a bit of a question. Because what I mean by pseudo-randomness is we can interact with a hash function, and you probably want to use it as a stand-in for Fiat Shamir. But we cannot supply arbitrarily large vectors to Fiat Shamir. I mean, we can, but at some point you'll be shooting yourself in the foot and spending more time computing hashing than assembling the polynomial if you would do so naively. And lastly, the last point is if you naively run over all the coefficients, there might be use cases where it still makes sense, but we generally want to avoid that because it's slow. All right, that closes my presentation. The floor is open now and indefinitely far in the future for questions. Feel free to send me an email at that email address. Nothing left to say on my part, unless in response to questions.
Thanks a lot, Alan. It was like very illuminating, as always. I really enjoyed your presentation. I think it was really clear. I think that in the case of the polynomial, can't you use directly all the evaluations and try to build just from the evaluations by using the interpolation theorem?
You can, but if you have k evaluations, they in the case that they correspond to a low degree polynomial or a polynomial of degree lower than k, then they uniquely identify this polynomial lower than k. But if this polynomial, if the polynomial that you're trying to construct has a degree far higher than k, well, then it's not constrained. You just find some polynomial that satisfies k linear constraints, where these constraints say it evaluates to this value in this point.
Okay, because I was thinking maybe on how to achieve sublinearity, and if you could use like vector instructions or something for evaluations.
Evaluations are really powerful and tempting to use for sublinear assembly of polynomials, but the problem is that they induce linear constraints. And so it's no problem at all for the attacker to find another polynomial that evaluates to the right points.
Okay, yeah, no, you would have to constrain the degree also. Okay. Any questions?
I have a question, but it probably is just a very silly question. I'm just asking myself, you know, all these zero knowledge protocols that are used in practice has perfect completeness. I was asking myself, why not just use a little bit of error on the completeness side to make it go faster? There's probably an exponentially an error that decreases exponentially and it gets exponentially fast to one. Well, why not use that in practice, or is it doesn't make any sense, right?
I think in practice that would make sense. When restricting attention to zero knowledge proof systems, I've never seen the possibility for this. I've never seen anywhere where it applies. But I have seen one very closely resembling use case for a what is it, negligibly small completeness error, and this is in the mutator set. So this is a cryptographically authenticated data structure. You can put items in, you can take items out, similar to a Merkle tree, except